In this video, we solve 14.3.009 from the Larson and Edwards Calculus Early Transcendental Functions textbook, 7th edition. We're given a double integral in polar coordinates. We're asked to evaluate the double integral and sketch the region R. And the evaluation is pretty straightforward. Remember, whenever you're evaluating a double integral, you do the inside integral first and you sort of work your way out. So we ignore this 0 to pi, we ignore the d theta for just a little bit, and we look at this integral inside. We're anti-differentiating r with respect to r, so we use the power rule. There's an implied 1 there. Add 1 to the exponent, divide by the new exponent, and then evaluate from r equals 0 to r equals 9 times the cosine of theta. It's just the fundamental theorem of calculus. If you want, you can factor out that 1/2. We end up with 1/2 times 9 cosine of theta, quantity squared, minus 0 squared, which is of course 0. Now here you can square the 9 and square the cosine, or you should square the 9 and square the cosine. So we're going to get 81 times that 1/2 is 81 over 2 times cosine squared theta, d theta. Now for this part, you might be tempted to use u substitution, and that would be a good thing because we've got cosine of theta being squared. So you might think of that as cosine of theta squared, or the same way that you see it right here, cosine of theta squared. But there is no du outside of those parentheses, those implied parentheses. There's no sine of theta or negative sine of theta anywhere. So u sub won't work. So you have to go back to our trigonometric integrals methods. There are guidelines that say if the power of cosine is even and non-negative, you should just use a power reducing formula. It turns out that this is 1/2 of 1 plus cosine of twice the angle. The angle was originally theta. So now it's 2 theta. And you're multiplying that by that 81 over 2. 81 over 2 times 1/2 is going to be 81 over 4. And then you've got this right here. And we've got a basic rule for that, and that's a k theta modification of a basic rule. So the antiderivative is pretty simple. The antiderivative of 1 with respect to theta is 1 times theta. The antiderivative of cosine is sine. Remember, you want to keep the angle the same. And if there's a constant multiplying your variable inside, you have to divide by that constant. If you're using the chain rule, you'd have to multiply by 2. When we're doing that backwards, we have to divide by 2. And this is a definite integral, so we evaluate this expression from 0 to pi. So we end up with 81 over 4 times this quantity evaluated at pi. That's pi plus 1/2 of sine of 2 pi. And then we've got 0 plus 1/2 sine of 0. Sine of 2 pi is 0, sine of 0 is 0. So really we just have 81 pi over 4. Okay, so that's the first part. It's not too bad. And the second part asked us to sketch the region R. Remember how this works. These bounds go with this variable, and these bounds go with this variable. So R is between 0 and 9 cosine of theta. And theta is between 0 and pi. And normally we would think of theta going from 0 to pi as starting here and then ending up over here. But that's actually not what's going to happen here because of this r equals 9 cosine of theta. Remember, if you see bounds like this, you're really thinking of 4 different functions. Theta equals 0, theta equals pi. Actually, theta equals 0 and theta equals pi are both the x-axis. because R is free to be anything. and then r equals 0, which is the origin, and r equals 9 cosine of theta, which is a little bit more interesting. So that's really what I'm going to focus on, and then we'll talk about this piece in just a second. So if I have r equals 9 cosine of theta, and I want to graph it, I could just pick values of theta between 0 and pi and see what happens, and then graph in the polar plane. I think it's easier though if I transform this into a rectangular equation. Now remember, with rectangular equations, we have formulas for r squared. We know that r squared equals x squared plus y squared. We know that x equals r times cosine of theta, and y equals r times sine of theta. Let me just write all of that down. I know it's a bad sign when I'm saying a lot of things out loud and I'm not writing them down. So we want to keep these identities in mind as we try to transform this equation into an equation involving only x and y. Notice I've got a cosine of theta over here and an r over here. One way that I can transform this using these identities is to make this an r squared. Now, one way you can get an r squared over here is to square both sides. Another way you can get an r squared over here is to multiply both sides by r. If you do that, you'll have r squared equals 9 times r times cosine of theta. And that's going to be much more helpful than squaring both sides, because now I've got an r cosine of theta, which I know is x. And r squared we know is x squared plus y squared. So what we have is x squared plus y squared equals 9x. Now that is a circle. It doesn't look like a circle yet because there's a 9x over here. There's no constant on this side, but that's okay. We can just move that 9x over here and complete the square, and we'll see that this is a circle. It's just not centered at the origin because of that 9x. In order to write this equation of a circle in standard form, we need to complete the square on the x. So we identify b, that's the number in front of the x, take half of that and square it. Since it's a fraction, I can just square the numerator and square the denominator. So I'm going to add 81 over 4 to this side. That's going to make that a perfect square. And that's legal as long as I also do the same thing on the other side. So over here on this side, this is a perfect square. It's x minus 9 over 2 squared plus y squared equals 81 over 4. And if you're wondering, how did I get that 9 over 2? I ask myself, what do I square to get the 81 over 4? It's going to be plus or minus the 9 over 2. And since that's a minus, that's going to be a minus. Or you can just remember it's always going to be that b over 2, that number right there that goes there. Okay, so this is a circle. It's centered at whatever you're subtracting from the x and the y. So this is centered at 9 over 2 and 0, since we're not subtracting anything from the y. The radius of the circle is related to that 81 over 4. That's the radius squared. So if you want the radius, you've got to take the square root of that, and you get 9 over 2. Or if you prefer, that's 8 over 2, which is 4, and then half. So it's 4.5. So I've got a circle centered at 4.5, 0. With a radius of 4.5. So it's going to look like this. X equals 4.5, y equals 0. And then I'm going plus and minus 4.5 units in the x direction. So from 0 to 9. And then plus and minus 4.5 units in the y direction. Now that's not our region, that's just one of our bounds. R equals this. And the other bound for r is r equals 0, so that's the origin. Now, if you're asking yourself, why is this 0 to pi? If it was 0 to pi, I would imagine it would be in quadrants 1 and quadrants 2. Like, shouldn't it be, if this is in quadrants 1 and 4, well, shouldn't the bounds be negative pi over 2 to pi over 2? You're absolutely right. We could represent this circle that way. We could let theta go from negative pi over 2 to pi over 2. And we would trace out all of the points on this circle. But we can also let theta go from 0 to pi, and it turns out we'll trace out all the points on this circle as well. So if r is going from 0 to here, so it's starting at 0 and going out to that curve, and theta goes from 0 to pi, it turns out to trace out that whole circle, and this is the region R that we're talking about. Now, I haven't proven it yet. I've just told you that that's what our circle looks like. Now let's talk about how this 0 to pi actually generates this circle if r equals 9 times cosine of theta. Now, one way you can do that, one way you can prove that to yourself is just by plotting some points. I know, doesn't seem particularly sophisticated. I'm gonna let theta equal 0, let's say pi over 4, pi over 2, and then 3 pi over 4, and then pi. And r is equal to 9 times cosine of theta. So when theta equals 0, we're gonna have 9 cosine of 0. Remember what your cosine curve looks like? At 0, cosine is equal to 1. So this is going to be 1 times 9, which is 9. At pi over 4, we get cosine of pi over 4 times 9. Oops, I wrote pi over 2. Cosine of pi over 4 is square root of 2 over 2. We're multiplying by 9. So I've got 9 root 2 over 2 here. We'll get a decimal approximation for that in a minute. And at pi over 2, we're going to be at 0. I wonder if you're saying, I don't know about that. Yeah, we'll see. We'll see how this plays out when we graph it in the polar plane. At 3 pi over 4, so that's going to be right here. Cosine is negative. It's a negative square root of 2 over 2. So we're going to have negative 9 times root 2 over 2 there. And at pi, a cosine is negative 1. So we're going to have a negative 9 there. And let me get my calculator so I can estimate that 9 times square root of 2 over 2. So that's approximately 6.3, 6.4. Okay, and I just chose 4 angles. I chose 0, pi over 4, pi over 2, 3 pi over 4, and pi. Pi over 4, that's this line. It's theta equals pi over 4 on that line. This is theta equals 0 on this line. This is theta equals pi over 2. And this is theta equals pi on this line. And theta equals 3 pi over 4 is over here. Okay. Now remember, when you're plotting in polar coordinates, we actually kind of do it backwards. We look for theta first, and then we go out this many units in the direction of that line, in the direction of that ray. So theta equals 0, that's right here. And if r is positive, we go in this direction. If r is negative, we sort of go backwards along that line. We go in the opposite direction. So when theta equals 0, if r is positive 9, that means I go 9 units in this direction. Plot a point. Then over here, when theta equals pi over 4, I've got 9 times the square root of 2 over 2, which we just said was about 6.4. So we go out 6.4 units in this direction. It's kind of hard to see. If this is 9, I'd say 6.4 is about there, approximately. And then at pi over 2, we're right here. So far, we haven't proved it really. We could use more increments for theta. We could subdivide this interval from 0 to pi into smaller pieces. But we started here, we ended up over here, and now we're back here. And I think that's the top half of our circle. Now, if you're wondering, well, well, how do we get zero, this interval from 0 to pi, giving us a circle over here? Well, let's keep going. Okay, at 3 pi over 4, we get negative 6.4 approximately for our R value. So since we're on the 3 pi over 4 line and R is negative, instead of going out in the direction of 3 pi over 4, we go in this direction, the opposite way. We go out 6.4 units in the opposite direction from that. And then when theta equals pi, if R is negative 9, if we had theta equals pi, R equals positive 9, we'd end up over here. But since theta equals pi and R equals negative 9, we go backward 9. So it's going to give us this. It's because of those negative values of R that letting theta range from 0 to pi actually gives us this circle over here. Now, I would recommend, if I see this circle, that I don't do this. I don't let theta go from 0 to pi. Instead, I think of this circle as being tangent to that line that was formerly the y-axis. And I think of theta as going from negative pi over 2 to pi over 2. So it starts here and ends up over here. Now, if you're saying to yourself, I'm not sure that's going to give me the same circle, let's check it out and see. I'm going to use the same increment as before. Just going pi over 4 units from negative pi over 2 to positive pi over 2. And remember what the cosine graph looks like? That's it. And at negative pi over 2, it's at 0. Okay, so we have 9 times cosine of negative pi over 2, which is 0. So R starts at 0. I think I'm going to graph this on the same grid here. Same set of coordinate axes, excuse me. I'm going to use blue now. So when theta equals negative pi over 2, so that's on this line, R equals 0. So we start at that point. Then at negative pi over 4, we get 9 times cosine of negative pi over 4. Cosine of negative pi over 4 is a positive number. It's positive square root of 2 over 2. So this is 9 root 2 over 2, which is approximately 6.4, like we said before. So now I'm going to go along the ray, theta equals negative pi over 4. Remember, this was theta equals 3 pi over 4. And then we went backwards about 6.4 units to get here. I can also think of that line as being given by theta equals negative pi over 4. And then I go positive 6.4 units in the direction of that value of theta. If R were negative when theta had this value, I'd have to go backwards, but since R is positive, I go forwards and I end up there. So at negative pi over 2, I was here. At negative pi over 4, I'm there. When theta equals 0, cosine of 0 is 1. So I have 9 times 1, which is 9. So I go on the theta equals 0 line, and I go out 9 units. So far I've traced out my circle this way. At pi over 4, we get 9 root 2 over 2 again, which is about 6.4. So I'm on the theta equals pi over 4 line. I go positive 6.4 units out that way. And at pi over 2, if cosine of 0, or cosine of pi over 2, which is 0, times 9, which is 0. So we end up here. So as theta goes from negative pi over 2 to pi over 2, we get that circle. Or you could do like they did in this problem statement. As theta goes from 0 to pi, I believe we traced out the top half of this circle. And as theta goes, or excuse me, as theta goes from 0 to pi over 2, we traced out the top half of the circle. And then as theta goes from pi over 2 to pi, that's when we would be over here. All those R values were negative, so instead of giving us points over here, they actually mapped over here because we were going on the negative part of that line. We've got a line, and when r is positive, we go in the direction of theta. When r is negative, we go in the opposite direction. We sort of go backwards along that line. So 0 to pi will work, or negative pi over 2 to pi over 2 will work. They give you the same circle. And that is how we sketch the region R.